Hi guys, so in this video I am going to present to you the proof for the Bolzano-Weierstrass theorem, and I already proved some of the lemmas that I'll be using in this video in the previous video. There were two primary lemmas that I'll be using in this video, and the first one was that every bounded sequence in R to the power of n has a convergent subsequence, and then there was a second one which said that a point X lies in the closure of a set S if and only if there exists a sequence in the set S which converges to X. So those are the two theorems that I'll be using to prove the Bolzano-Weierstrass theorem. So let's see what the Bolzano-Weierstrass theorem says. It says let S be a subset of R to the power of n, then the following are equivalent. S is closed and bounded, which means S is compact. So this essentially means that S is compact. And this is true if and only if every sequence of points in S has a convergent subsequence whose limit lies in S. So this is the theorem that we want to prove. Now, before I move on and before I write out the proof for this theorem, I would like to emphasize upon the fact that this is not really the precise definition of compactness. It's more appropriately named sequential compactness. There's another theorem, it's called the Hein-Boyle theorem, that deals with compactness itself in higher level analysis courses. So yeah, and this theorem essentially defines what it means for a set to be sequentially compact, but we'll overlook that for now. Okay, so let's just go ahead and begin the proof. So notice first of all that we need to prove this theorem in two directions. We first need to prove that if S is closed and bounded, then every sequence of points in S has a convergent subsequence whose limit lies in S. And then we need to prove it in the other direction. We need to assume that this is true and then show that S is closed and bounded. So let's begin. I'm going to prove I'm going to write out the proof, and I'm going to prove it in the other direction first. So proof. So I'll first prove it in this direction. In other words, before I even start with this, let's just define what S is. Let S be a subset of R to the power of n. So first I'll prove it in this direction. So I'll assume that S is closed and bounded So I want to show every sequence of points in S. So every sequence in S has a convergent subsequence whose limit lies in S. So I'm gonna write this out a little bit differently. So I'm gonna say that for every sequence A of n, that is a subset of S, there exists a subsequence. Let's say that's A of n of j, which is also, of course, a subset of S, such that A of n of j, such that as j tends to infinity, let me just bring this down right here. A of n of j tends to, let's say, a point L, and we can say where, or let's just write it out over here, L is an element of S. So this is what we want to prove. You know what, I'm just gonna get rid of that j equals to infinity. So this is what we want to prove. We want to prove that for every sequence in S, there exists a subsequence which also lies in S, such that the subsequence converges to a limit that lies in S. And the only two things that we can use is the fact that S is closed and then the fact that S is bounded. So yeah, let's go ahead. So the first thing, let A of n be a sequence in S. Then, as S is bounded, as S is bounded, we know that there exists ns, or there exists a subsequence of a of n, or of the sequence a of n of j. Oh, sorry, the sequence a of n, my bad. Of the sequence a of n, which converges. Let this sequence be a of n of j. Also, let L be the real number, or let L be an R to the power of n, be the limit of sequence A's of n's of j. Okay, so two things. What we have already showed so far is the fact that S is bounded. So we use the fact that S is bounded, and the lemma that we proved in the previous video, which said that every bounded sequence in R to the power of n has a convergent subsequence. This is clearly a sequence. It is since S is bounded and the sequence lies in S, the sequence is also bounded, and thus by that theorem we know that there exists a subsequence that converges or that has a limit. Now, the only thing that we need to show is that this limit lies in S. However, if you think about it, this was the other lemma that we proved in the previous video, which said that a point X lies in the closure of S if and only if there exists a sequence of points in S that converges to X. So we already proved this, and I'm actually just going to use a version of this theorem to prove that L must lie in S. And the thing that we need in order to do that is the fact that S is closed. So as S is closed, note, as S is closed, and because the sequence A of n of j lies in S, it follows that L is an element of S. L is an element of S. And of course, this is true because, or by theorem, I'm going to label this theorem 1.3, or theorem, let's say let's label this as 2.3. So this theorem was in my second video by the Bolzano-Weierstrass theorem, and it was the third theorem I proved over there, which said that a point lies in the closure of S if and only if there exists a sequence of points in S which converges to that point. So I'm using that in the opposite direction. So what I'm saying is A of n of j is a sequence that converges to L, and since A of n of j is a sequence that lies in S, it follows that L is also in the closure of S. But since S is closed, we know all of the boundary points of S are a subset of S, and therefore L must also lie in S. So just to re-emphasize the proof so far, because we have proved one of the directions, we just need to prove the implication in the other direction. So we assumed that S is closed and bounded, and we wanted to show that every sequence in S has a convergent subsequence whose limit lies in S. So what we said is let A of n be any arbitrary sequence in S. Now we use the fact that S is bounded to show that basically to show that every sequence in S has a convergent subsequence by the first theorem that I proved in my previous video, which said that every bounded sequence in R to the power of n has a convergent subsequence. Since every sequence in S, that is S of n, any arbitrary sequence, is bounded, it follows that every arbitrary sequence S of n has a convergent subsequence. And we said, let this convergent subsequence be S of n of j. And we assumed that L is the limit that it converges to. It's a convergent subsequence, so and L is any arbitrary element of R to the power of n. So we assumed that L is what this limit converges to. The last thing that we wanted to show is that L is actually an element of S. That is the last piece that we needed to prove. Now, in order to show that, we used the third theorem that I presented in my previous video, which said that a point lies in the closure, let X be a point in R to the power of n and S be a subset of R to the power of n, then X lies in S if and only, X lies in the closure of S if and only if there exists a sequence in S that converges to X. Now, what I did is I'm using this theorem. Essentially, what I said is S of n of j is clearly a sequence in S, and clearly S of n of j converges to L. Therefore, it follows by that theorem that L must be an element of S. So this is the proof of the Bolzano-Weierstrass theorem. It's half of the proof because we just proved the implication in one direction, but the other direction is actually just extremely similar. So in this case, when I'm proving it in the opposite direction, I'm actually going to use the contrapositive. I believe you can write a direct proof. I also believe you can do a proof by contradiction. I'm just going to prove it by contrapositive. So I'm going to assume S is not closed or not bounded. One of those two conditions are true. So either S is not closed or S is not bounded. And in this case, I want to show, okay, let's just paste this over here. Okay, so now in this case, I basically want to prove the negation of this. So I want to show that there exists a sequence in S of n such that for all there exists a sequence in S such that every subsequence of that sequence either does not converge or it converges to a number that does not lie in S. So I'll either show that S of n of j converges to a number. Let's say that number, in this case, I'm just going to use some other letter. Let's say it's m, and m does not lie in S, or S of n of j does not converge, or the sequence S of n of j does not converge. In either case, if it does not converge or if the limit does not lie in S, it violates this part of the theorem. Okay, so let's begin. So first of all, what I'm going to do is I'm going to assume that S is not closed, because remember, there are two possible cases that we need to analyze. The first case is what happens if S is not closed, and then the second case is what happens if S is not bounded. Now that I think about it, it's actually probably easier to prove what happens if S is not bounded, so that's what I'm going to do first. So S is not bounded. So let's say assume first, case one, S is not bounded. S is not bounded. Then it follows that there exists a sequence in S which diverges to infinity or negative infinity. So we've assumed now that S is not bounded, and of course that means that there exists a sequence in X which diverges to infinity or to negative infinity, then every subsequence of this sequence must also diverge to infinity or negative infinity. And thus we've shown that there exists a sequence in S such that for every subsequence A sub n of j does not converge. Okay, so let me just really quickly explain you why this is true. Most of this will basically be an exercise for you guys to try on your own. If you have a sequence A of n, and if you assume that A of n converges to, or sorry, diverges to infinity, then a very quick epsilon delta, basically epsilon delta argument will show that A of n of j, which is where A of n of j is any subsequence of A of n, will also diverge to infinity. I'm not going to prove that. That's a very elementary result that you can prove very quickly on your own just by using the definition of a limit of a sequence converging to infinity or diverging to infinity. Okay, so that's the first part. Now let's assume now case 2. Now in this case we're going to assume that S is not closed. S is not closed. Okay, now if S is not closed, what this essentially means is that the boundary of S is not a subset, or well, it doesn't even, it shouldn't even be boundary of S. What I should say is that the boundary of S intersection with S is equal to the empty set. So in other words, S contains none of its boundary points. In that case, it's not closed. Okay, so here's the thing now. The way we are going to prove this is we're going to assume that we have a point X that lies on the boundary of S. What we're going to show then, or what we're going to show next, is that there exists a sequence in S that converges to that point X. Of course, if that point converges to X, or if that sequence converges to X, every subsequence of that sequence must also converge to X. And we'll basically prove that this must be true then, because X of course is not in S, because X by assumption is in the boundary of S. Okay, so let's begin. What I'm going to say first is let X be an element of the boundary of S. Then, as S is not closed, it follows that X is not an element of S. So that's the first thing. Second, note, consider as X is in the boundary of S, it follows that for every epsilon greater than 0, the ball centered at X with radius epsilon intersection with S is not equal to the empty set, and the ball centered at X with radius epsilon intersection with S complement is also not equal to the empty set. We won't be using this. This is what we really want to use over here. So now what I'm going to do is I'm going to construct a sequence that that converges to S. Then consider the following sequence. Consider the following sequence. So A sub 1 is equal to, so now what I'm going to do is I basically want to pick a point that is 1 unit away from X, or anything less than 1 unit away. So that will work. So what I'm going to do is I'm going to say let A sub 1, so A sub 1 is defined as follows, shouldn't say equal to. So A sub 1 is defined, you know what, let's just do n equals 1. For n equals 1, we have A sub 1, actually I guess it's just better to do it this way. So here's how I'm going to define A sub 1. I'm going to say A sub 1 is a point in the ball centered at X with radius 1 and ace of 1 is also an element of S. Of course, this is always possible to do. Both of these conditions can always be satisfied simultaneously because of the fact that the ball centered at X with any arbitrary epsilon, with any arbitrary radius, intersection with S is not equal to the empty set. So I can just arbitrarily say that the radius that I'm picking is 1. Then for ace of 2 is basically any element of the ball centered at X with radius 1/2 such that ace of 2 also lies in S. And then you continue this process inductively and you say that ace of n is defined in the following way. It's in the element, it's an element of the ball centered at open ball centered at X with radius 1/n such that ace of n also lies in S. Then the sequence ace of n is clearly a subset of S. Also, as n approaches infinity, or in fact, I should say for every n in the set of natural numbers, the distance between ace of n and X is less than or equal to 1/n. Thus, as n approaches infinity, the absolute value of ace of n, the norm of ace of n and X minus X converges to or goes to 0, which implies that ace of n converges to X. Thus, then every subsequence of ace of n must also converge to X. Okay, so once again, I'm not going to prove why this is true. This is also a very, very elementary result. It's actually extremely similar to this piece over here, that if a sequence diverges to infinity or negative infinity, then every subsequence of that sequence will also diverge to infinity or negative infinity. And in this case, it's basically the same theorem. It says that if a sequence ace of n, it's a modified version of the theorem. It says that if ace of n is a sequence that converges to a real number L, or any number, it doesn't even have to be an element of R. Ace of n can be a sequence in higher dimension and it still holds. So let's say this is in R to the power of n, or R to the power of m, where m is any arbitrary natural number. Then every subsequence of ace of n, let's say ace of n of j, will also converge to L. Without this, actually, it will also converge to L. It will converge to the same number. So that's a theorem that you can prove on your own. It's a very, very simple epsilon delta argument once again. But this completes the proof. So then, note, as X is not an element of S, we have shown, or I will say we have completed the proof. We have completed the proof. So yep, that is the proof of the Bolzano-Weierstrass theorem. That is the entire proof. So just to emphasize about the second part of the proof real quickly. The second part, basically what we wanted to show, or what we had to show, is that every sequence of if every sequence of points in S has a convergent subsequence whose limit lies in S, then S is closed and bounded. What I did instead is I presented a proof by contrapositive. So I assumed that S is not closed or it's not bounded, and then I wanted to show that there exists a sequence ace of n in S, such that for every subsequence of ace of n, let's say that's ace of n of j either converges to a number that does not lie in S, or it does not converge at all. So the first thing we assumed is S is not bounded. That's the first case. And we know that if S is not bounded, that then there must exist a sequence in S which diverges to infinity or negative infinity. And then every subsequence of this sequence will also diverge to infinity or negative infinity, thus showing what we wanted to show. The second case, and probably the longer case, is what happens if S is not closed. If S is not closed, then essentially we pick a point that lies in the boundary of S, and since S is not closed, we know that that point does not lie in S. We then constructed a sequence which lies in S and which converges to X. This construction is actually quite similar to the construction that to the construction of the sequence that I used in my previous video to prove the third theorem that I used earlier on in this video. Anyhow, once we had constructed the sequence, we showed that the sequence converges to X and that the sequence lies in S. And since the sequence converges to X, we know that every subsequence of this sequence will also converge to X, but clearly X is not an element of S, and that completes the proof. Basically, we've shown what we wanted to show. So yep, that is the Bolzano-Weierstrass theorem. Why is this important? We'll be using this theorem to prove the extreme value theorem. I'll also use this theorem to prove the intermediate value theorem. It's a very important theorem of its own, but most of its application, at least in second year analysis courses, lies in proving the extreme value theorem and the intermediate value theorem, which I'll be doing in the upcoming videos. There is another lemma that I need to prove first. I'll probably do that lemma and the extreme value theorem together. The lemma is the theorem that says that every a continuous function maps compact sets to compact sets. So I'll be proving that, and then I'll be proving the extreme value theorem, and then eventually the intermediate value theorem. So yep, that's all. Let me know if you have any questions, and I'll see you in the next video.